live. Got it. Is it good? Okay, good. I guess we can keep it in the background. Oh. Let me do it over here. Oh. Oh, come on. Not the right one. Yeah? Say it again? I start. Okay, okay, that's great. Yeah. Okay, we'll start in a couple of minutes, I think. Actually, in a minute. Whenever I get my live thing, we'll start. Okay, good. Okay, welcome everyone to our lecture 13. This is kind of a midpoint of the semester, actually. I think we'll have 26 lectures and 13. By the end of this, we'll reach the midpoint. And before the Easter break, we'll hopefully cover 15 lectures. And today, we're going to go into even more exciting topics. And we're going to improve the performance of the designs that we have been looking at in the past 4 or 5 lectures, the microarchitectures. And I'm going to give you a reminder. And we're going to cover pipelining. Essentially, all processors today are pipelined, and they do sophisticated pipelining. And we'll see the first example of it today, and probably tomorrow as well. Okay, just to remind you, you have the Moore's Law paper to review if you want extra credit. And these are some guidelines. And this is our agenda for today and next few lectures. Last week, we covered microarchitecture fundamentals. We talked about single cycle, multi-cycle microarchitectures. That's great. This week, we're going to finish, hopefully, pipelining. We'll see. We may need to actually do some of it next week also. And hopefully next week and the week after that, we will cover out-of-order execution. But there will be an Easter break in between. So out-of-order execution will be kind of partitioned across the Easter break, let's say. Does that sound good? And we're going to focus only on microarchitecture now. We're assuming the von Neumann model at the ISA. Okay, these are some readings. Your books, unfortunately, don't cover this material as much. Actually, pipelining is okay, maybe. Pipelining issues, they don't go into a whole lot of detail. So these readings are quite light, I would say. But I will still follow Harris and Harris for much of this lecture. Next week, when we go to out-of-order execution, unfortunately, your books will not be enough at that point. They cover other things that we don't cover. So we're going to essentially look at other readings. This is one of the good readings that talk about microarchitecture of superscalar and out-of-order execution processors. So we will see that next week. So just to review, this was a single cycle MIPS processor we built, if you remember from last week's lectures. And hopefully you know how it operates. It's at a data path. It has the orange control signals and has a control logic, which generates the control signals. And we actually covered everything. There should be no magic here. Because you know how every component operates here, basically. You should be able to look into the register file and you know what a memory looks like. You should be able to look at memory, you know what a memory looks like, a multiplexer. So all of its operation is built from the ground up, from the transistors as we started, right? So it should be no magic at all. Now we can really execute instructions on the single cycle MIPS processor. And then we ask questions, of course, about this. This was the other single cycle MIPS processor in your book. You can study it also. It's very, very similar to this. And then this is the finite state machine of the single cycle MIPS processor. As we said, everything happens in a single cycle for a given instruction, and instruction transforms architectural state to architectural state prime. And we discussed the downsides of the single cycle processor. It's contrived. It doesn't work very well. You have to optimize for the worst case all the time. Basically, it breaks all of the microarchitecture and architecture design principles. So we asked the question, can we do better? And we said, yes, if you remember. So we built the multi-cycle MIPS processor that looks like this, essentially. Which essentially says that an instruction can take multiple cycles, multiple clock cycles to execute. And those multiple clock cycles are whatever it's needed for a given instruction. An instruction can take 1,000 clock cycles. Another instruction can take 1 clock cycle if possible, or 3 clock cycles. Now you actually have a lot more freedom to optimize the performance of this machine. So we thought it was beautiful, as we discussed. And this is a finite state machine. It's much more complicated because now different instructions actually follow different states, if you will. This is fetch over here. It's one state here, but you can break it into multiple states as well. This is decode. And then different instructions follow different states after that. And then we discussed trade-offs related to it. What is the shortcoming of this design? Well, first of all, the upside is you could keep adding instructions to this finite state machine by adding states, by adding data path elements, and by adding control logic as you need to execute the instruction. But we discussed that shortcoming is there's limited concurrency, as we will see in a little bit. And the hardware cost, actually the hardware cost is quite good, but limited concurrency was one of the shortcomings, as we will also see today. And we also discussed the assumption about memory in this particular finite state machine, at least it takes 1 cycle basically. In 1 cycle, you assume that memory gives you the result. Actually, in pipeline processor, we're kind of going to assume that, but we're going to handle it easily. So we said that this can be easily extended by saying if the memory did not provide you the result yet, the instruction or the data, then you basically stay in a particular memory access state until the memory provides you the result. Basically, you can keep staying in a state for thousands of cycles if you want, until the memory says, oh, I'm done, here's the result. And the memory sends you a control signal saying, I'm ready. And that ready signal enables you to transition from a memory access state to the next state in which you will do something with the data that's provided by the memory. So basically, this is also not magic because we've discussed finite state machines, right? This is just a bit more complicated finite state machine that goes from state to state to state to state based on control signals and what is happening in the system, meaning what instruction you're fetching. Okay, everything is good so far? So it's good that nothing is magic, basically. Nothing should be magic in this course because we started with an abstraction of the transistor and we basically build up to this. So whatever we're going to do today is also not going to be magic. Basically, we're going to ask the question, can we do better? And in terms of performance, and that's what will bring us to pipelining. So we've discussed these limitations, so I'm not going to go through this question again. And you may think about other limitations perhaps, but multi-cycle design is not perfect. One big limitation is limited concurrency, meaning you have this nice data path, but some hardware resources are idle during different phases of the instruction processing cycle. I'm going to highlight some of them. For example, when you're doing fetch, when an instruction is being decoded, fetch logic is idle. When an instruction is being executed, decode logic and fetch logic is idle. So you have these hardware resources, but you're not using them. An instruction is going through the hardware resources in different cycles. And a lot of the hardware resources are idle, essentially. For example, most of the data path is idle when a memory access is happening, right? You're accessing the memory. So let's take a look at this picture over here. This is the data path picture. You're accessing memory over here. The rest of the data path is idle, right? Register file, nobody's using it. ALU, nobody's using it. PC, program counter, nobody's using it. You can basically think of it that way. Okay, even though the hardware resources are not a lot, it's small compared to a single cycle processor because you don't have to replicate the resources as we have discussed last time, they're still idle. So basically the key question we ask is, can we actually do better? We have all these idle hardware resources, can we use them and maybe add some more hardware to improve the concurrency? Because we want to improve performance, right? That's the idea right now. Basically, that's the goal. More concurrency will lead to higher performance. In other words, higher instruction throughput, higher number of instructions you process in a given cycle, or more work completed per cycle, right? That way you can finish the programs faster also potentially. Okay, so the key idea is this basically. It's very simple, and that's the key idea of pipelining. When an instruction is using some resources in one of its processing phases, process some other instructions on the idle resources. So we have instruction X at program counter X using in the execute stage, for example, process instruction X plus 1 or the next instruction, next sequential instruction in the decode stage. Right? That's the idea basically. So let's go through this. When instruction is being decoded, you can fetch the next instruction. Right? When instruction is being executed, you can decode another instruction and fetch the next instruction. When instructions be accessing data memory, you can execute the next instruction, decode the next instruction, and fetch the next instruction. And basically, you keep doing this. When an instruction is writing its result into the register file, access data memory for the next instruction, execute the next instruction, decode the next instruction, and fetch the next instruction, basically. Right? So you see what's going on basically. We're pipelining the processing of instructions. That's why it's called pipeline. Or it's an assembly line of instructions that you're feeding into the machine. And each of the instructions is a different stage of the assembly line. Okay, so hopefully this is intuitive and simple. And now we're going to talk about basically what are the issues related to this pipeline. But before we go into that, let's take a look at this pictorial a little bit. So this was our beautiful instruction processing cycle, right? These are the stages normally instructions go through. We kind of reduced that to 5. Again, it doesn't matter. You can combine some of them together. So this is what we did actually in the multi-cycle processor, if you remember. Fetch, decode, and register operand fetch, execute and evaluate memory address happens at the same cycle, same stage, let's say. Memory operand fetch and store and write back results. So these are the 5 different stages. And we're going to build a pipeline that consists of these 5 different stages today. It doesn't have to be 5. You can have a pipeline that's 30 stages or 40 stages or 50 stages. But of course, it becomes more complicated. Or you can have a pipeline that's shorter, like 2 stages, fetch and execute, for example. And you can combine some of these in those 2 stages. But we're going to look at a 5-stage pipeline. So basically, this is our multi-cycle machine, if you remember what we constructed in the last lecture. So what we're going to try to do is, when the blue instruction is writing its results, we're going to have another instruction, a yellow instruction, doing address calculation or doing something in the ALU. Another instruction, the decode stage, another instruction, fetch stage. Here, I don't exactly show the memory access. I have 4 over here, but we'll do 5, as you will see soon, because it was not as easy to color the memory access stage because there's a single memory, as you can see over here. So we're going to change that with pipeline. So that's the basic idea. I think this is a powerful picture because it tells you that different instructions are in different parts of the machine, and they're being processed independently. But of course, life is not as simple, meaning you cannot take a multi-cycle machine and chop it up like this. It won't work. Why? We need to be much more careful because your registers are, for example, as we discussed in the multi-cycle machine, instruction register doesn't get loaded until you go to the next instruction. So you need to do something else over here. So this instruction, which instruction does it specify now? So you cannot really chop up the machine like this. You need to add more registers so that you know which instructions are being processed in different stages. So we're going to increase the hardware cost clearly compared to multi-cycle machine. And that's basically that's going to be one of the shortcomings of pipeline. Does that make sense? At least the basic idea? Okay, good. And this basic idea should be very familiar because we're going to see real pipelines as well. So, okay, basically, more systematically, the idea is to pipeline or assembly line the execution of multiple instructions. It's a bit slow. The analogy is assembly line processing of instructions. I mean, we see assembly lines in factories today. I'm going to give you actually some pictures of real assembly lines from 1908, from Henry Ford's factory, for example, right? That's the basic idea. We're going to pump in instructions from the front end of the machine and pump out the instructions from the back end. And instructions go through the same pipeline, except in different stages, different operations will be done on the same on the different instructions. Basically, we divide the instruction processing cycle into distinct stages of processing, ensure there are enough hardware resources to process one instruction each stage. If it's the fetch stage, we ensure that enough processing resources exist. If it's the memory access stage, we ensure that enough processing resources exist. And they don't conflict with each other, different stages, because these instructions in different stages are going to be processed concurrently. And we process a different instruction each stage. This is important, not the same instruction, different instructions. And instructions consecutive in program order are processed in consecutive stages. So basically, now you can say, we're now going to violate the von Neumann model at the microarchitecture level, right? Because von Neumann says you process only one instruction at a time. You move to the next instruction after the previous instruction is complete and has updated the architectural state. We're going to say no. To improve performance underneath, we're going to process multiple instructions before prior instructions finish. But we're still going to obey the von Neumann at the interface level, at the ISA. Basically, we're going to update the results only when an instruction finishes at the end. Okay, so we'll see that. So the key benefit, as we discussed, is it increases instruction processing throughput. Remember, cycles per instruction is how many cycles it takes to process an instruction. Here, hopefully by processing more instructions, we're going to have more we're going to be finishing more instructions per cycle. So for example, actually, I'll give you an example. In a non-pipe, in a multi-cycle machine, you finish one instruction every 4 cycles, let's say. Here, our goal will be finishing one instruction every cycle, because we're going to put one instruction into the pipeline every cycle. Hopefully, we'll get out one instruction in the pipeline at the end of the pipeline. Okay, we're going to look into this equation also. So downside, start thinking about this. Basically, clearly, this is not going to be, like with any idea, this is not going to come for free. We need to be very careful. And sometimes we may not be able to increase the instruction processing throughput because the pipeline and the programs are not going to be perfect, as we will see. Instructions will be dependent on each other. There will be control flow dependencies like branches. Start thinking about those. But also, we'll need to increase the hardware cost because of what I said over here, and ensure there are enough hardware resources to process one instruction each stage. Okay, so let's see that. So let's first see the benefits over here. So this is our multi-cycle machine. If you, again, hopefully you remember our multi-cycle machine. This is basically, I'm assuming we're executing 4 independent add operations. They have nothing to do with each other. In a multi-cycle machine that's designed in one way, an add operation takes 4 cycles per instruction, meaning you basically fetch takes 1 cycle, decode takes 1 cycle, execute takes 1 cycle, and write back into the register file takes 1 cycle. Okay, that's reasonable, right, for an add, as we discussed in last lectures. If you're a multi-cycle machine, you basically take 4 cycles per instruction, as you can see, and you finish this program in 16 cycles, assuming it's only 4 adds. But if you're pipelined, the idea is you don't do this. You basically increase concurrency, meaning when the first instruction is being decoded, you fetch the next one. When the first instruction is executed, you decode the next one, you fetch the next one. And when the first instruction is writing its result back, you're executing the next one, decoding the next one, and fetching the next one. At this point, you've kind of reached the steady state because our pipeline is 4 stages, let's say: fetch, decode, execute, write back. In this case, I've divided it that way. And there's 1 instruction every stage. This is called the steady state of the pipeline. The pipeline is full, basically, nicely going on. So if you look at this picture, you're really, in 4 cycles, you're finishing 4 instructions. Basically, once the pipeline becomes full, you're finishing 1 instruction per cycle, as you can see. This instruction is finished at the end of the cycle. This instruction finished at the end of the cycle. This instruction is at the end of the cycle, ... So if your pipeline is full, you're much, much faster than a multi-cycle machine. You can count the number over here, 4 plus 7 cycles as opposed to 16 cycles. But as your pipeline is in steady state, the speed up is actually much higher. Because here the steady state is 4 cycles per instruction. Here the steady state is 4 cycles per 4 instruction. You should really get a 4x speed up out of this. If life is always beautiful, of course. Unfortunately, that's not true. So basically, you can also think of this as 1 instruction is completed per clock cycle. Here, 1 instruction is completed per 4 clock cycles. But as we will see, life is not always this beautiful because, well, we will see multiple reasons, but instructions may not be independent of each other. That's one of the key issues, actually, we're going to tackle. And instructions may not be only operate instructions. They may be control flow instructions. What if somebody changed the program counter, right, in the instruction? What do you do to the pipeline at that point in time? And then how do you divide the pipeline into different stages? Is it going to be as perfect as I showed you over here? Are they going to be balanced? So there are a lot of interesting questions, basically, even with a pipeline processor design. So that's why we're going to spend some time on this topic. But let me give you an analogy. There are a lot of analogies over here, but one of the books that we don't cover in this course, the Patterson and Hesse book, actually gives this laundry analogy, and I like it a lot. That's why I use it. But it's the same issue. Let's assume that you have 4 loads of laundry. You haven't done laundry in a while, and you have 4 loads of laundry. Essentially, you can think of this as a multi-cycle machine doing laundry, right? You basically have 1 load. It needs to be washed, and then it needs to be dried. And then you need to fold them and you need to put them in the cabinets. And these are sequential steps, right? In this multi-cycle machine, you finish 1 load after 2 hours, as you can see, assuming each step takes 30 minutes. And then you move on to the next load, right? So every load goes through the same steps, basically. Do the washing. When the washer is finished, do the drying. When the drying is finished, do the folding, unloading and folding. When the folding is finished, put the clothes away into a cabinet. And if you're a multi-cycle machine, you have to, if you start your laundry at 6 p.m., you're going to be awake until 2 a.m., as you can see. So it sounds pretty bad, right? This doesn't sound very smart. That's the downside of a multi-cycle machine. So this is very similar to an instruction pipeline in some sense. Steps to do a load are sequentially dependent. You can think of this fetch, decode, execute, write back, kind of. There's no dependence between different loads in this particular case. This is going to be different than an instruction pipeline, as we will see. But you can think of these as 4 independent add operations. Then it's very similar. And different steps do not share resources. For example, in washing, you don't need the dryer. In dryer, you don't need the folding, whatever you're using for folding. In folding, you don't need the cabinet. You need it afterwards, right? So basically, the steps do not share resources. That's critical also. So this is a perfect, let's say, process to be pipelined, right? And let's take a look how to pipeline it. Basically, we can do 4 loads of laundry in parallel. This is our pipeline. It's a 4-stage pipeline: washer, dryer, folder, and taker away. Let's say those are the 4 stages. And at the steady state, basically, once the washer ends, we move to the dryer the first load, but the second load goes into the washer. And then once the dryer ends, we move the second load into the dryer, and we at that point, hopefully, because these are equal amounts, hopefully the second load ends in the washer, and then you put the third load into the washer. So this is very similar to the 4 independent add instructions that I showed you earlier. So you don't need any additional resource in this particular case. You're kind of lucky. Your throughput increases by 4. Latency, so throughput increases by 4, meaning you're finishing 1 load every 30 minutes, right? As opposed to 1 load every 2 hours, as you can see. That's the throughput. But latency per load is the same, actually. So 1 load actually still takes 2 hours, but you're starting the loads much earlier, right? You didn't reduce the latency of a load. You just increase the throughput of many loads. So that's the difference between throughput and latency. Never confuse these 2 concepts. They're fundamentally different. Throughput is how many loads or how many instructions you're finishing per given time. Latency is how long it takes to finish 1 load or 1 instruction. Here, we're improving the throughput, as you can see. Okay, any questions on this pipeline? Okay, so now let's take a look at a culprit. Usually, in my experience, a culprit is a dryer. That damn dryer always takes a little longer. And if it takes 1 hour, you have a problem with your pipeline. So that's the multi-cycle. Your dryer takes 1 hour. You're up until, I don't know, 4 a.m. or something. So don't do that. But if your dryer takes 1 hour, it also disrupts your pipeline, because now you cannot start the second load to dry. So you have some wasted time over here, as you can see, right? Yes, you can start the washer over here, but you still need to wait until this dryer finishes the first load. So basically, your pipeline looks like this. As you can see, you're up until 11:30 a.m. 11:30 p.m. Sorry, at night. So basically, the slowest step, 1 hour, the dryer that takes 1 hour decides the throughput of your pipeline. As you can see, as a result, your throughput reduces. And this happens also in real machine pipelines also. So, for example, memory access takes 2 cycles for some reason. What do you do about it? Well, what can you do about it? Anybody? Yes. that's one option, yes, but that requires more resources. I'm asking for a simpler answer. Anybody? Anybody wants a better dryer? That sounds good, right? Get a faster dryer. That's one option. It may be costly. It may be too expensive to get the faster dryer, right? Yeah, faster dryer gets you back to this. That's nice, but it may be very costly to get that faster dryer. Okay, you cannot do that. You're stuck with this dryer that's not fast, that's slow. Can you still restore the throughput? Any other idea? Yes? Exactly, double the number of dryers, right? Have dryer A, dryer B, still cheap. Hopefully it's cheaper than a much faster dryer. And when you alternate the usage of the dryers, basically, when the first load is in dryer A, second load can safely go to dryer B. And the third load now can go to dryer A because dryer A is ready by the time you actually finish the washing of the third load. So this is actually used in real machines also, basically. You can restore the throughput by using 2 dryers. Now you can still do 2 loads per hour. That's the throughput, actually, if you look at that. I think so. If this is wrong, let me know. Okay. Yeah, basically, that's the idea over here. Does that make sense? Okay, good. Okay, yes, it's 2 loads per hour because we're finishing 1 load every 30 minutes. That's what I'm trying to read over here, decode while I'm looking at the slide. So this is correct, basically. That's the throughput. You're finishing 1 load every 30 minutes in the steady state over here. So this is a very common thing. So if your memory is slow, for example, you can have 2 memories that are potentially cheap. Okay, so this is a real life pipeline. Has anyone seen this picture? This is actually one of the experimental pipelines Henry Ford did in 1908, I believe, to decide whether they want to pipeline the entire assembly line of Ford cars. And the guinea pig was this part, that was this component in the pipeline called magneto. it basically supplies ignition energy to the engine before generators became common. And you can read this. I'll read this actually. It was a complex and innovative component that was one of the early Ford Model T's technological advantages. And this was integrated into the engine's flywheel, and it involved many pieces. And you can see that those many pieces are being assembled by people in an assembly line, pipeline over here. Basically, you're feeding, let's say, magnetos over here, or magnetos that are not ready yet. And then everybody is putting something onto the magneto in a pipeline. And initially in a multi-cycle machine, or whatever you would like to think, under the old system, as you can see, a worker could assemble 35 of these in a 9-hour shift, or roughly one every 15 minutes, right? But they actually tested this, and they actually really implemented in 1913, as they say over here. And then they specialized the workers also, so they actually improved the efficiency as well. So you can see that they reduced the assembly time to 5 as opposed to 15, and they also reduced the workforce. So this is a real life pipeline. It's different from an instruction pipeline, but it has similarities, right? And it has also inspired other things like this. Have people seen something like this? It's a magneto from X-Men, and you can see the inspiration over here, right? Yeah. Okay, and today's assemblies are actually much more sophisticated, as you can see. But this is really a pipeline also. Different parts of a car is processed in different stages of the pipeline. So when some of these robots are assembling the tires, in another stage of the pipeline, the robots are assembling the engine. In another stage, some robots are assembling some other part of the car, and you can divide the processing into 1,000 stages where 1,000 different things are being done on a given car. And the car moves slowly through the pipeline, but the throughput is very high. Okay, and I will show you an example of a early machine, one of the early machines that had a pipeline, and you can see this IBM Stretch. This machine is actually responsible for fetch, decode, and execute. Those names were provided by this machine. This is not the first machine that implemented pipelining, but it has a lot of influence because it actually named the stages nicely, fetch, decode, execute. And you can see that Gene Amdahl is the key designer, and only 9 units were sold. Compare that to today's machines. And you can see the price is a bit higher, right, than what you would pay for a cell phone. And you can see the power and the weight. You don't want to carry this, basically. And it only has 2 megabytes of memory. Okay, you can read about this. Okay, so let's take a look. So I'm showing you these earlier pipelines because assembly line of cars is more or less an ideal pipeline. So what's an ideal pipeline? Our goal is to increase throughput with little increase in cost in case of instruction processing hardware cost. In an ideal pipeline, basically there are 3 properties. We want to repeat identical operations, meaning the same operation is repeated on a large number of different inputs. For example, all laundry loads go through the same steps, right? All cars go through the exact same steps. Yeah. In an instruction pipeline, that's not completely true, actually. It's true that most instructions go through the same steps, but there are some steps that some instructions don't require. For example, there may be a memory stage in your pipeline, memory access stage, and your add instruction doesn't require that, right? We've actually seen this earlier as well, so I'm not telling you anything new. So you kind of have some wasted time in your pipeline by having the add instruction go through that memory access stage. So that's why instruction processing is not an ideal pipeline. I'm giving you an example. I'm going to analyze it in more detail later on. So an ideal pipeline has repetition of independent operations. Basically, there's no dependency between one load and another load. They're conceptually independent. You don't need to, you can completely reorder them, for example, right? But that's not true for an instruction pipeline. That's true for a car also. There's no dependency between the first car that you assemble and the second car and the third car, fourth car. You don't need to finish the first car before you can start the second car. There's no such dependency in an ideal pipeline like this, right? But instructions are not like that. The third instruction that you fetch may be dependent on the first one because it may require a value that's produced by the first one. That's why an instruction pipeline is not an ideal pipeline. And then the third property is uniformly partitionable sub-operations. This is a mouthful phrase. But basically, this means that processing can be evenly divided into uniform latency stages that do not share resources, ideally. So basically, every stage takes X cycles, let's say, or X time, and they do not share resources. This actually can be true in a laundry. Well, laundry actually has this basically. You can make it uniformly partitionable, hopefully. It requires some effort, actually. But they do not share resources, basically, in the laundry case. Assembly line of cars, again, it also has this property. Uniformly partitionable, you need to be careful about the evenly divided part still in those ideal pipelines, but you can make that happen. in a computer, a computer pipeline, it's actually much harder to do this. As we will see, do not share resources is going to be a bit hard. We'll need to replicate some of the resources, and there will be some sharing of resources, as we will see soon. And division into exactly the same amount of time in each pipeline stage will be a lot harder also, as you will also see. And these are actually things that are not easily solvable. Actually, division into perfect, how should I say, perfectly equal amount of time in pipeline stages has been shown to be NP hard also. Okay, so basically an ideal pipeline is much closer to automobile assembly line and doing laundry, but not so much the instruction processing cycle. I'm kind of giving you a head of what instruction processing cycle looks like. So now we're going to examine it a little bit more. So let's take a look at ideal pipelining, and we're going to look at instruction processing right now. So assume that this is a one cycle instruction processing, and this register can be exactly the same as this register. For simplicity, I actually put them different, fine. So basically you have some combination logic over here and some sequential logic over here. And it takes t picoseconds to actually execute an instruction. It could be any instruction, let's say. So if in ideal pipelining, if you want a two-stage pipeline, ideally you have two divided by two picoseconds over here, 2 divided by 2 picoseconds over here, and you don't need to increase the amount of time. So if you look at the combinational delay, it's still t, but we're not going to be able to achieve that perfectly. This is really assuming perfect partitioning. And throughput hopefully is 2 over t. Basically, you finish 2 instructions every t cycles, right? Every t units of time. So this is ideal. And if you actually keep increasing the pipeline stages, you divide the t into the number of pipeline stages, t over 3 in this particular case. And you should be able to do that nicely with your combinational logic. It may not be perfect. Remember, some paths are not easily divisible in combinational logic, depending on what you're trying to do. For example, you may not be able to partition your memory nicely. Here, I just said execute on memory and write back. How do you partition that? It's not easy, basically, if you think about it. But this is an ideal pipeline, as I said, right? Ideally, you would keep increasing the throughput linearly as you add number of stages. But we know that that's not real. But because partitioning will be a problem, and also you add sequencing overhead, right? These latches do not come for free. So now you can see multiple problems. Your time is increasing because these latches do not come for free. Your time may increase because this may not be exactly t over 2 picoseconds. You may need to add some more time so that you can balance and partition. And you're adding hardware cost to add more registers, right? So as you keep increasing your pipeline depth, the number of stages, today's pipeline, some pipelines are actually 30 stages. Some pipelines are more 15, 16, 17, 18 stages, much longer than these. You're adding overhead in terms of both time and hardware cost. So let's take a more realistic pipeline because of this. So this is a non-pipeline version, as I said earlier. Throughput is really it's not 1 over t, it's really 1 over t plus s. S is the register, sequential logic delay. Remember the timing and verification lecture? Sequential logic has some timing delay, including the register hold and setup times, as well as clock skew, because this is synchronous. So you need to account for that. And if you have a k-stage pipeline version, assume that this is still t over k. We're perfectly balancing the pipeline. Nice. That's not true, as we said, but we're assuming that. So basically, your throughput of a k-stage machine looks like 1 divided by t over k plus s. The sequencing over it still stays the same. And ideally, minimal gate delay is 1 gate delay, and this is your ideal throughput. So you basically approximate 1 divided by 1 plus s. Okay, so your throughput can be very high, basically. In the end, you're dominated by your sequencing overheads. If this is 1 gate delay, this may actually be equal to that, or more than that. Okay, so basically the takeaway over here is that register delay reduces the throughput because you have sequencing overhead between these stages. And also, this picture is still not fully realistic. This picture still assumes perfect division of work between stages, t over k. If that changes, this t picoseconds overall here, maybe let's say t plus, I don't know, maybe 1.5 t, right? And that actually reduces your throughput also. And we will see that when we look at a performance example of pipelining at the end of this lecture or tomorrow. Does this make sense? Okay, so this is the throughput. Let's take a look at cost now. So this is the non-pipeline version with combination of costs. Assume that you have G gates over here and you have R registers. That's the register cost. Your cost is G plus R, roughly again. We're doing analytical equations over here. K-stage pipeline version, ideally, you would have G over K. Ideally, I would say, because it's very difficult to divide, for example, to 30 stages where you perfectly divide the G gates into G divided by 30, right? You normally need to add a lot more, as we will see, actually. So that's, but even if you assume that, your cost, G gates still remain the same, but your register cost is linearly increasing with the number of stages. You get R times K, as you can see. So this is costly, even if you just look at the register cost. So registers increase the hardware cost, and this picture ignores resource and register replication that's needed. Basically, G over K is really not G over K. It's G over 0.5K, maybe, I don't know. Maybe 2G over K, I don't know. It depends on how you balance things. And also, RK is maybe an underestimate because you need bigger registers, as we will see, to do control signals and other stuff. So basically, your cost is actually increasing more than what I show over here. Does that make sense? Okay, and we will now build the pipeline and see how that cost increase. We're not going to calculate the cost exactly. We're going to look at latency at the end, as I said, but cost is something interesting to look at. Okay, so let's jump into building this machine that pipelines the instruction processing. Again, this is a reminder, this is our instruction processing cycle. This is another view of it. And this is the 5 stages that we discussed earlier. And we're going to build a machine that has these 5 stages in a pipelined way. And we're going to start with a single cycle microarchitecture. Actually, it turns out single cycle microarchitecture is a better place to start for pipelining a machine than a multi-cycle, because multi-cycle reduces the resources significantly. Whereas in a pipeline machine, you will need to, if you think about it, in a single cycle, you need to use all parts of the machine in a single cycle microarchitecture, right? Because an instruction has to go through all parts, well, in a worst case instruction needs to go through all parts of the machine. Here, in a pipeline machine, you're really using all parts of the machine in a single cycle, except different instructions are in different parts of the machine, right? That's why it resembles a single cycle machine more than a multi-cycle machine, because a multi-cycle machine, in a given cycle, you're using only a fraction of the resources. Okay, so basically, let's start with the single cycle microarchitecture, and we're going to divide this T into multiple stages and hopefully improve throughput. So our control signals are going to be very similar to the single cycle machine, actually. We're not going to change a lot, except we're going to add registers, as you will see, pipeline registers, because you need to separate the instructions that are processed in different stages. But before we go into pipeline registers, let's first, how do we divide things into stages, right? Even that's an issue. As I said, you need to perfectly balance the work. And this is, again, a simple example of dividing things into stages, 5 stages. As I said, we'll look at 5 stages. One instruction is being fetched, another is being decoded, another is being executed, another being accessing memory or calculating, well, here it's execute or calculate address, here it's memory access, and here it's write back, basically. So if you look at this, if you do this partitioning, this is 100 picoseconds. And this is 100 picoseconds because register file access may take 100 picoseconds. The other ones require memory access or ALU, and we just said 200 picoseconds over here. So this is not a perfectly divided pipeline. We just violated ideal pipeline principle over here. But it's not easy, basically. And you need to have the resources so that you can write to the register file over here. So basically, we're going to have these loops. These loops are going to cause headaches to us, actually, in the pipeline, as we will see. So ignore these loops for now, but keep in mind that in a single cycle machine, if there's a loop that looks like this, meaning a result is being communicated in some later part of the machine to the earlier part. Now, how do you do that becomes important, right? For here, we need to update the program counter. When do you do that and how do you do that? Here, we're going to update the register file. When do you do that and how do you do that? Because you don't want to update the register file here. So one of our assumptions will be we're going to update the register file at the end of the pipeline. So instructions update the register file when they go to the end. This is going to help us maintain the von Neumann semantics. Instructions are not going to update the register file in an out of order manner. And the memory will be updated in this stage, basically. Okay. And we're going to look at issues related to memory updating when we talk about precise exceptions. So there are many questions over here, actually. But one question is this the correct partition? If I want to have a 5-stage pipeline, is this the best I can achieve? Meaning, my clock cycle is dominated by 200 picosecond stages over here, and I have 5 stages. And this is a good question to ask always. Maybe you can pipeline the machine much better, basically, right? But I'm not showing you that. And also, why not have 4 stages or 6 stages? Why not have different boundaries, right? Why not have the clock cycle 150 picoseconds and have a different partitioning, maybe more equal? Again, these are good questions to ask. There's both science and art related to this, which we're not going to cover, but we're going to assume that this is what we're given at this point. but you can think about, critically think about the fact that this may not be the best design based. Okay, assume that this is our design that we were given or that you did. Let's analyze this throughput a little bit. So basically, this was our multi-cycle machine or single cycle machine. I mean, it could be multi-cycle also depending on how you do it. But basically, we're finishing one instruction every 800 picoseconds over here because we're assuming 800 picoseconds is what it takes to execute an instruction. Your clock cycle is, if it's a single cycle machine, your clock cycle is 800 picoseconds, for example. Okay, that's not bad. And with pipelining, we do better, but we're finishing one instruction every 200 picoseconds, right? Because each stage takes 200 picoseconds. Even though some of the stages can finish in 100 picoseconds, you cannot do that because each stage has to be equal, right? Otherwise, you have a problem at hand. How do you synchronize between different stages becomes problematic, for example. So even though, for example, okay, why is this so? Even though this takes 100 picoseconds, you still need to wait for 200 picoseconds because it's a synchronous system, right? We're going to add registers later on, as we will see. Okay, so here we've lost throughput basically just because of the way we designed the pipeline. Remember, we have 800 picoseconds. Ideally, we should have a throughput increase of 5x, right? But we're getting a throughput increase of 4x here. Why? Because we didn't balance the pipeline nicely, meaning the number of each stage takes 200 picoseconds as opposed to 160 picoseconds, right? Ideally, you would have 160 picoseconds over here. Yes, 160. Okay, does that make sense? Okay, and this is an issue, as we will see. And real machines have this issue also. The real machines don't necessarily have exactly the same delay critical path in each of these stages. Okay, so let's take a look at how do we enable this pipeline processing. So keep this in mind. I'm not going to discuss this partitioning of the pipeline even more, but this is actually a really interesting science and art. It becomes even more potentially problematic if you have a 30-stage pipeline, for example. Intel Pentium Proscott, for example, in 2004 or so, or 6 or so, it had 30 stages. It was one of the deeper pipeline machines. And today we're not, I think there are not a lot of machines with 30-stage pipelines, but we're not 5 stages also. We're 16, 17, 18, 22, maybe 25 in some cases. Sometimes they're not disclosed also. Okay. So how do you enable this pipeline processing? We need to have registers, pipeline registers, because you need to isolate the different instructions that are executing in different parts of the machine. So this is our single cycle machine, simple version. So we're going to add pipeline registers. And this is, if you look at the bottom, we're going to divide this T into T over K as much as possible. 5 stages in this particular case. So these are the pipeline registers, basically. They look nice. And we name them as, this could be called the fetch stage register, but instruction fetch / instruction decode register, instruction decode / execute register. Basically, they take the name of the stage previous to it and the stage after it. Execute / memory register and memory / write back register. So you need 4 registers. And for example, what is in these registers is of course the question, right? In this first cycle, here you're fetching one instruction. At the end of the cycle, you latch something, right? And then you of course have the program counter, which is a register as well that was already there anyway. So at the end of the cycle, you have the instruction register and PC+4 because you may need it later for branching or something else, updating the for something else, exception handling, as we will see later on. But basically, at the end of the stage, you have the instruction in the in this pipeline register. In the next cycle, this instruction is going to be decoded as well as it will access the register file, right? That's that stage. Very similar to what we have done earlier, except this is happening. While this is happening, PC+4 is being fetched because PC+4 was incremented while this instruction that you're decoding was here in the previous cycle. And then this instruction, after it gets decoded, you have some signals over here that you put. You also read the register file, you put the register values over here, and you put the immediate over here. So the pipeline register keeps growing, as you can see, right? As we will see, it'll grow even more with control signals. This is just a data path right now. And while in the next cycle, you'll start processing this instruction in the execute stage or address calculation stage. It could be, as you can see, there are resources for both. And then the next instruction gets decoded over here, and then the next instruction is being fetched. And then basically ALU produces a result, you put it over here. There's some B register over here that's used for stores over here, as you remember, potentially. And then there's an XPC that you may use. And then the memory stage is over here. The data that you get out of memory is put into this register over here. And then the ALU alt is put over here also, because you want to write the results into the register file at the end, at the last stage, as we discussed, to preserve the one-Neumann semantics. So this is very similar to what we did with single cycle, except we're latching the results at the end of each cycle, as you can see. And these pipeline registers are actually occupy more stuff, as we will see soon. Does this make sense? Okay, I see some nods. That's good. Yes.
So if we're jumping, for example,
yeah.
we calculated in XMEM,
we
calculated there.
Yeah.
What do we do if we jump the instructions going with the pipeline?
Exactly. Yeah, exactly. We'll talk about that basically. That's an example of, that's called the control dependence. So if this was an instruction that was branched, what do you do next, right? Basically, if you fetch the instructions sequentially, then you need to flush them. You need to invalidate them. And we're going to talk about that actually. And we're going to talk about branch prediction or conditional branch prediction a lot later on. That's a very good question. But we're not there yet. So basically, no resource is used by more than one stage. That's the key over here. As you can see, data memory and instruction memory is separated over here. And no resource is really used by more than one stage. You need to have enough ports to the register file so that you can write back to the register file while reading from the register file also. Okay, so hopefully that's clear. Because if a resource is used by more than one stage, you have a problem, right? And we will see that problem in a little bit actually. Okay, so all instruction classes must follow the same path and timing through the pipeline stages. We're going to take a break after 5 minutes. So as you can see, load word is being fetched over here. Load work is being decoded, load work is being executed, load work is accessing memory and writing back. Load word is a good example because it goes through all the stages. But an add instruction, for example, does not have to go through this memory stage, but it will, because that's the pipeline, right? So basically, there is a performance impact because some instructions go through stages they don't need to go through. But this is very similar to what we have discussed earlier as well. So let's take a look at pipeline operation example. This is a nice case. A load word and subtract are flowing nicely. I'm just showing you 2 examples. But again, life is not that beautiful because subtract may be dependent on the load word. And this actually poses a big problem in this pipeline, as we will see. Okay, I'll go through some of these quickly because hopefully these are kind of obvious. This is another view of the pipeline operation. You're filling the pipeline with different instructions. At some point, pipeline is full. And hopefully you keep your pipeline full. But it's not going to be as easy to keep them full if there's a branch instruction, for example, as you mentioned, or if there are instructions that are dependent on each other. So that's the steady state for us. And this is another view. So you can study this on your own. It's kind of boring, but this is steady state basically. In steady state, if you can keep your pipeline full, you get 1 instruction out of it per cycle. That's good. So let's take a look at the control points in a pipeline. Basically, these are the control signals. I just added them over here. And we essentially have the identical set of control signals as the single cycle data path. So nothing has changed basically, because we have to do the exact same operations. We just need to, we have a register write signal, for example. We need to enable it whenever we're writing to the register file. We have a memory write, memory read signal. We have an ALU operation signal. Basically, we have to enable these signals at the correct point in time right now, because you don't have a single instruction in the machine. You have 5 instructions in the machine potentially. And you need to use the correct control signals for the for each instruction at a given stage. So basically, this register write signal needs to really come from the instruction that's really writing to the register file, which is here, right? It should not come from the instruction that's being decoded. That's the idea over here, which hopefully makes sense. So basically, control signals are the same as single cycle machine for a given instruction, but control signals are required at different cycles depending on stage. Hopefully that's obvious. And there are multiple options to do this basically. One option is you can decode once at the decode stage using the same logic as single cycle and buffer the signals until they're consumed. This is best seen as pictorial like this. In the decode stage, you have control logic that decodes the instruction and partitions the control signals as control signals that will be needed in this stage, execute stage, in the memory stage, and the write back stage. And you basically propagate the control signals to the appropriate stage and get rid of the control signals that you don't need anymore. This is what your registers kind of look like in that case. So here you propagate the control signals that you need for the memory stage and write back stage. And then you consume the control signals that are needed for the memory stage and the memory stage over here. And then you propagate only the control signals that you need in the write back stage and then get rid of the memory signals over here. So this is what your control signal propagation looks like. And hopefully it makes sense. So there are control signals that you use in different stages and you should carry them with the instruction as the instruction proceeds in the pipeline. And you can get rid of the control signals that you don't need anymore, obviously, right, to save hardware. Or another option is don't decode the instruction completely. Don't generate all of the control signals. Generate only the control signals that you're going to use in the next stage with logic that's embedded in the previous stage. That's the idea, basically. So decode locally. So either you decode globally over here and propagate all of the control signals to wherever you need them, or do incremental decoding locally. And which one is better is an interesting question. I don't expect you to answer this because it's a complicated question. Clearly, if you decode once and propagate, some of your registers will be huge because you may actually have a lot of control signals over here, right? Progressively, they will reduce because you don't need some of them after some point. So that's the downside of it. But there's an upside. You generate your control signals early. Control signal generation may not be on the critical path anymore. Whereas if you do it locally, you need to generate the control signals as you go through, and you need to make sure it doesn't go on the become your critical path. And when you change the pipeline a little bit, that may cause a mess, basically. So conceptually, option one is nice because control signal generation is almost all done in one stage, and then you propagate, but it comes with a hardware cost, basically. So which one is better has a trade-off question, essentially. Okay, so let's take a look at these pipeline control signals. This is essentially the pipeline machine in full almost. You can see that, see the exact same structure that I showed you over here, and you need to use the control signals at the right points. So for example, this is the write back control signals. Register write signal that I mentioned to you has to be coming from this stage. You cannot, because you need to, if an instruction is writing a register, it should be writing the register in the write back stage. Okay, so that's an example over here. So here's this is from your book. This is the single cycle machine from your book, pipeline machine from your book, very similar to what we're looking at. But basically, you cannot use the register write signal over here. Basically, this is not the register write signal, sorry. This is the write register signal that goes into the, this is the register ID over here. So you cannot use it from here because you need to write to the register with the instruction that's writing back over here. So this write register ID should also come from the write back stage, right? So you can easily make mistakes if you're not careful in a pipeline control. So this is the fixed version, basically. This is the correct pipeline data path. You need to also propagate the write register ID over here and use it whenever you're actually writing to the register, which is in the write back stage. Basically, all control signals must arrive at the same time as the result, as well as the write enable signal, right? Okay, so hopefully this is obvious, which means that your control unit looks again like this. This is all of the control signals are generated over here as much as possible, unless they're dependent on data path execution with branches. We have seen that, but most of them are generated, as you can see, and they're propagated. Okay, basically the control needs to be delayed to the proper pipeline stage. Never forget that when you're pipelining a machine. If you forget that, you'll get the wrong result. Okay, so this is a good place to stop and take a break, and then we're going to go into more detail on pipeline execution. Not me. Okay, let's get started. There's one question over here which says, is it safe to say a pipeline is not balanced if one stage is taking much shorter than others or shorter than others? And yes, I would say yes. That kind of pipeline is not perfectly balanced, basically. You need to, if you want a perfect pipeline, you really need to have equal amount of time in each of the stages. And there's mathematical analysis of this, actually. People mathematically analyze this a lot. It becomes much harder, of course, when your machine becomes much more complicated, 30 stages, 40 stages, etc. But yeah, balance is defined that way, essentially. Okay, remember an ideal pipeline. I will not go through this, but we're going to examine the instruction processing pipeline in terms of these identical operations, independent operations, uniformly partitionable sub-operations. Hopefully you have a good intuition of what these are in the laundry or the automobile assembly pipeline. But basically, instruction processing pipeline is not an ideal pipeline in any of these, let's say, dimensions. Different instructions, they do not all need the same stages. Basically, they're not necessarily identical. And we force different instructions to go through the same pipeline stages. And this leads to what's called external fragmentation. Some pipe stages are idle for some instructions. Instructions still going through it, but it's doing nothing useful. Essentially, this is wasted work and wasted energy also. But you cannot do much about it because it's the design of the pipeline. Some modern machines make the pipeline heterogeneous, meaning at some part of the pipeline, you start specializing for the instructions, but then that's not what we're talking about over here. And that makes the hardware cost even higher and more expensive, basically. Okay, uniform sub-operations, I think we've already seen this. Different pipeline stages are not exactly the same latency. I mean, they have to be the same clock cycle, but they don't necessarily have the same latency for useful work that they're doing. And you need to force each stage to be controlled by the same clock. This leads to internal fragmentation, meaning some pipe stages waste some work. They're fast, but they still need to obey the clock cycle time dictated by the longest pipeline stage that's doing useful work in that amount of time. As a result, some part of the clock cycle is wasted in some pipeline stages. And actually, this is a lot. This happens a lot in machines. Almost always, a good chunk of the, well, a good chunk. If one pipeline stage is a longer critical path than other pipeline stages, you waste the clock cycle in other pipeline stages. That's why you cannot perfectly partition the work also. And independent operations, instructions are actually not independent of each other, and we're going to focus a lot on this today and tomorrow. So one instruction may be dependent on the prior instruction's results. And as a result, you need to somehow detect and resolve inter-instruction dependencies to ensure the pipeline provides correct results, right? So far, we've assumed instructions are independent. But if this changes, you basically have pipeline stalls, meaning pipeline is not always moving. An instruction needs a result from a later instruction. Later instruction has not generated its result yet because it didn't go to the right result stage. As a result, an instruction needs an instruction from an earlier instruction, meaning earlier instruction in the pipeline. But that earlier instruction did not write its result yet. So this instruction needs to wait, meaning you need to stall the pipeline for some amount of time. Okay, so these are the issues in pipeline design, basically. How do you balance the work in pipeline stages? We're not going to talk about that anymore. How many stages and what is done in each state? But we're going to talk a lot about keeping the pipeline correct, moving, and full. And you really want all of that. Correct is correctness issue, of course. Moving and full is performance issue. In the presence of events that disrupt the pipeline flow. And there are many events that disrupt the pipeline flow. Dependencies, for example, data and control dependencies between instructions. Resource dependencies, resource contention. We will see one example of it. And long latency or multi-cycle operations. So we actually seen the resource contention example with the dryer, right? We have a resource contention between two different instructions and we multiply the resource. So that's one way of handling the resource contention problem. Long latency operations we're going to talk more about when we talk about out-of-order execution, for example. They always cause a problem. We're going to assume in the rest of this lecture that memory takes one cycle, but always keep in mind that memory doesn't take one cycle. If it takes 10 cycles, 100 cycles, the pipeline needs to stop, right? You need to wait for memory. So what do you do in that case? Your throughput actually reduces drastically whenever you need to go to memory, if it doesn't take one cycle. Okay, we're going to talk about handling exceptions and interrupts. That's the next lecture or next lecture. And improving pipeline throughput, essentially. How do we minimize stalls? That's going to be part of this lecture. Does it sound good? Do people know about this? Yes? No? Did you cover this in any course? I see no. Maybe some people see somewhat. Is there any course that covers this? Okay, maybe not. Okay, good. So let's talk about causes of pipeline stalls. So what is a stall, first of all? Let's define this clearly. Basically, it's a condition, any condition when the pipeline stops moving. I mean, not all the pipeline needs to stop moving. Some part of the pipeline stops moving, basically. You cannot move this instruction to the next stage because it requires something that has not been produced yet, or it requires a resource that's busy, right? So as I said, this is due to multiple reasons, which hopefully will appear. Oh, okay. This is due to basically three major reasons: resource contention, data and control dependencies between instructions. These are dictated by the program semantics, and long latency multi-cycle operations. Basically, the second part is dictated by the program semantics. You have to obey them. And the third one are because of the hardware design, usually. And you still need to make sure the pipeline works correctly and with high performance in the presence of these. So let's talk about these dependencies, the program semantics part first. This is also called a dependency. Your book uses hazard. I don't like the term hazard because hazard is something that's not semantics. The program semantics is dependence, right? The program says this instruction should get its value from R1, which is produced by this other instruction. That has nothing to do with the hazard, right? Hazard is something like scary, right? It's a hazardous condition. This is just pure dependence. You're communicating values. That's not a hazard. Hazard is a condition when you that happens when you need to be extremely careful about handling it. Yes, when you're designing the pipeline, you need to be careful, but the fundamental thing is not a hazard. It's really a dependence in the program, and we all have dependence in our programs. And dependencies dictate ordering requirements between instructions. Clearly, there's a higher level program semantics, and the programmer wrote this program such that there's some ordering between the instructions. And there are two types of ordering: based on data flow or data dependence, and based on control flow or control dependence. These are the control instructions, like conditional branches, case statements, switch statements, etc. Resource contention is also sometimes called resource dependence. In this case, it's okay, I think, because you're really depending on the same resource to execute an instruction, but it's not a semantic dependence, basically. It's a more hardware dependence. So basically, it's not fundamental to the program semantics, so we will treat resource contention separately. But let's get it out of the way first. We're going to talk a lot about the semantic program dependencies. Let's get the resource contention out of the way so that it's clear. So basically, resource contention happens when two instructions in two pipeline stages need the same resource, right? That's the issue. I mean, it also happens when one instruction in the same pipeline stage needs multiple resources, but we've kind of handled that in single cycle, multi-cycle architectures as well. It's the same thing. But if two instructions in different pipeline stages need the same resource, there are multiple potential solutions. One is eliminate the cause of contention. Clearly, this is hopefully obvious. Actually, both of these are obvious. But basically, how do you eliminate it? You duplicate the resource, for example, as we did with a dryer, right? Or you increase its throughput somehow. Basically, reduce the time it takes for it to produce a result. For example, you can use separate instruction and data memories, or caches, as we will see. And that's what we will do, basically. In the fetch stage, we have an instruction memory. In the memory access stage, we have a data memory, as we see. Or you can use multiple ports for memory structures like register files, right? We have two read ports and one write port for the register file. And the write port is used in the write back stage, and read ports are used in the decode and register file access stages. So these are examples of eliminating the resource contention. And we're familiar with it, hopefully. And the second thing you can do is detect the resource contention. Say, okay, I don't have money, or I cannot increase my cost to do the first one. So I'm going to live with a single memory. And if you do that, you need to detect the resource contention and stall one of the contending stages. Meaning, you say, okay, this stage, this instruction, this stage should use the resource, and this instruction, this stage should use the resource in the next cycle. And in the meantime, the pipeline should stall this instruction that is not going to get the resource, should not move on in the pipeline. So the question is, which stage do you stall? And you should always stall the younger instruction, because the later instruction is really blocking the pipeline in the end. So the later instructions, meaning later instructions in the pipeline, older instructions in the program sequence, clearly. So don't stall the things that are going to go out of the pipeline first. And that's usually a good principle, basically. So for example, what if you have a single read and write port for the register file? Only single port, you can use it for reads or writes. One instruction at the end of the pipeline, write back stage, is trying to write to the register file. Another instruction is trying to read from the register file in the decode stage. Which one do you stall? Well, you stall the one in the decode stage so that the instruction that's writing to the register file goes away, right? Out of the pipeline, basically. Okay, so this is solution 2 is clearly not desirable. And with resources like memory and register file, almost all instructions use these. I mean, all instructions use the memory for sure. Almost all instructions use the register file. Not all instructions write to the register file, yes, so you don't have the write read issue. But that's why you need, solution one is employed very heavily for commonly used resources. If a resource is not very commonly used, you can use the second solution. So remember the common case principle of microarchitecture. Again, you can employ the solution you choose based on that common case principle. Is what I'm seeing a common case? Does it happen 80% of the time? Or does it happen 1% of the time? If it's 1% of the time, maybe second solution is not too bad for your performance, right? And this is again, Amdahl's law. Okay, so let's take a look at a common resource dependence, which is the register file. So these are independent, completely independent instructions. Hopefully, this is from your book. I didn't complete the verified this year, at least. But basically, if you look at this, we fill the pipeline. In cycle 5, this load instruction is, let's see, this load instruction is writing to the register file, and this AND instruction is reading from the register file. If you have a single port to the register file, read and write, this is a resource contention. But in our assumption, in our pipeline, load instruction can write, and another instruction can read 2 registers. So in fact, we have 1 write port and 2 read ports. So we eliminate this resource contention by applying solution 1, replicate the ports. Right? And this dependence is very common, as you can see, right? At least in this program, once the pipeline is full, every single cycle, you have this dependence. When one instruction is writing to the register file, another instruction is reading from the register file. That's the reason why we replicated the ports over here. Okay, so I'm going to make some assumptions that your book also makes in the remaining part of this pipeline design. And this is one assumption. The register file can be read and written in the same cycle. And the way it operates is writes take place during the first half of the clock cycle. So this load can write to the register file in the first half. That's why this is half over here. And read takes place during the second half of the cycle. So there's no problem between these 2 instructions, even if they're dependent on each other. So if this load is writing a value that this add and needs, in this case, it doesn't need it, fine. But even if it needed it, it would be fine, because we're assuming in the first half, the value is written to the register file by the load, and it's available to whoever reads the register file in the second half of the cycle. So reads take place during the second half of the cycle. This is a trick. This is done in real processors as well. This will help us by reducing the stalling, as we will see. But the downside is operations that read or write to the register file have only half a clock cycle remaining to complete. So what does this mean? Basically, if you're reading over here, you only have a half a clock cycle. If you want to do something more over here, you have only half a clock cycle to be able to do that, right? Okay, so this will be more clear when we look at some examples soon. But keep this in mind. We're going to eliminate some issues with data dependence by enabling the register file to be written in half of the cycle and read in the other half of the clock cycle. Does that make sense? If you didn't do that, then you can basically say this register file write takes full clock cycle and the value is available in the next cycle. Clearly, this will reduce your performance a little bit. Here, we're making the value available in the middle of the cycle so that someone else can be in the same stage and read it in the same clock cycle, right? That's the idea. That's the benefit of this. Okay. Okay, now let's take a look at semantic dependencies. Basically, resource dependency is not semantic dependence. It depends on a resource. But semantic dependencies are data dependencies. And there are 3 types of data dependencies. If you're taking a compiler course, you will cover this very well. But one is flow dependence. And this is the only true data dependence, basically. Meaning you have a read to a location after somebody writes to a location. And this is exactly the same location of memory or registers. Basically, you're communicating value from one instruction to another. Anti-dependence is you have a write to a location after somebody reads from that location. This is not semantically a data dependence because, or data flow dependence, because you're not communicating a value. You're using that location to store something else when you write to it after someone else reads from it. Output dependence is write after write. Basically, you have the same memory location or register location. One instruction is writing to it, another instruction is also writing to it afterwards. So the second 2 are kind of weird, right? They're not really communicating between instructions. That's why they're not true data dependencies. These are called false dependencies also. So we'll take a look at that basically in a little bit. But actually, any one of these can cause stalls in a pipeline machine. For all of them, you need to ensure semantics of the program is correct. You cannot ignore them, basically. If you do something wrong, you may actually get the wrong result. So flow dependencies always need to be obeyed because they constitute a true dependence of a value, as we will see in a little bit. Anti and output dependencies exist because you don't have enough names in the you don't have enough registers, for example, or you don't have enough memory locations. So one instruction is reading from register R2, another instruction later writes to register R2. Well, technically and semantically, the second write has nothing to do with this read, right? I mean, they may be dependent on each other in some way, but this particular reading to R2 and writing to R2 has no relation to each other semantically. You're writing to R2 because you don't have any other location to write to, perhaps, because you have a limited set of register file. Makes sense, right? So if you didn't have a limited set of register file, you can eliminate anti and output dependencies completely because they're not inherent to the communication of data between instructions in a program. That's the key realization, and you will hopefully realize this. Even if you don't realize it exactly at this point, you will realize it later on because whole concept of out-over execution builds on this. Okay, so basically these two dependencies are false dependencies because they're dependent on a name and not a communication of a value in the end. And we will later see what we can do about them. We're going to be a lot more aggressive about them, basically, and get rid of them as much as possible. Whereas flow dependence, you cannot get rid of them, unfortunately, because one instruction is producing the value and then another instruction is consuming that value. You have to communicate that produced value to the consumed value correctly. Okay, so let's take a look at this pictorially. These are like some abstract operations, as you can see. This is the real dependence, flow dependence. So the second instruction is reading register 3 that's written by the prior instruction, register 3. So you'd better get the correct value of register 3 over here. Anti-dependence, the first instruction is reading from register 1 in sequential order. The second instruction is writing to register 1. Technically, these instructions have nothing to do with each other, right? As you can see, right? This is just reading register 1 and producing some result. This is writing into register 1 some result that has nothing to do with this instruction. So technically, this could be R1000. But here, if this is R1000, this also has to be R1000. That's the difference between these dependence types, right? So output dependence is also very similar to anti-dependence. For example, here, this instruction is writing to R3. It's read by some other instruction, but look at this other instruction. It's also writing to R3. It's write after write. Again, technically, these instructions have nothing to do with each other, right? I also mentioned that they are not dependent on each other in some transitive way through other instructions, as you can see. Again, you can safely rename this register to R1000 without changing this R3 at all. And that's a very good litmus test. Can I rename the register? Can I assign another register to this particular register without changing some other another instruction's output register or input register? You cannot do that over here, but you can do that over here. That's why these are false dependencies. But they have to exist again because we have limited number of general purpose registers and we have limited number of memory locations also. Even though memory may be very large, if your data set is much larger than memory, you will see a similar problem in memory as well. With registers, only 32 registers, right? You will have this problem. Okay, so let's take a look at this. I mean, we've already seen this basically. What if the sub were dependent on load word? Would they be able to flow like this? So load word is executing here. It's calculating its address. Sub is dependent. When load word moves to memory, can sub move over here? Well, I don't think so, right? Because load word subtract did not get the right register value if it moves over here. So it'll operate on the wrong register values because load word did not update the register file yet. So load word will update the register file over here. So sub has to stay over here until load word updates the register file. That's the idea. Okay, and we're going to see that more basically. So that's called data dependence handling basically. And again, your book covers it somewhat. If you want to get a very good treatment of it, this nice survey paper, overview paper, that overviews how modern processors operate, covers it a lot more. Okay, so as I said, anti and output dependencies are easier to handle. You write to the destination register only in the last stage and in program order. That actually handles those dependencies. Take my word for it for now. You will see that as we go through it. But flow dependencies are more interesting and challenging. And that's why people have developed many ways of handling these flow dependencies. And there are 6 fundamental ways. We're going to cover all of them throughout this course. One way is you detect the dependence and wait until the value is available in the register file, which is what I just said over here, right? The sub instructions waits until the value of the load is written into the register file. Okay. That's detect and wait. That's one approach. That's low performance. Or you can detect and forward or bypass the data to the dependent instruction whenever the data is generated. Meaning you don't wait until the data is written to the register file, but maybe the data is generated at the end of the ALU execution stage. You basically bypass it through a separate path to the instruction so that the instruction gets it earlier than the register file write happens. So this is higher performance. This is called data forwarding bypassing. The third one is detect and eliminate the dependence at the software level. The compiler, the programmer looks at the instruction and says, oh, this pipeline cannot execute this the way it's written. So I'm going to reorder the instructions. I'm going to insert no ops to make sure that all instructions get the correct values when it's executed on this pipeline. So we're going to see this. And here, there's no need for the hardware to detect the dependence in this case. So it's beautiful also. And this is also employed in existing systems. And then we're going to talk about detecting the dependence and moving it out of the way for independent instructions. This is going to be out-of-order execution. We're going to very briefly talk about predicting the needed values, executing speculatively and verifying. This is going to be more and more complicated. Okay, you don't have the data value. What do? You don't want to stall the subtract. How about I just predict the value? Maybe the value is 0. I say, okay, this register value is 0. This other register value is 5. I'm going to do the subtract, continue, and at the end, I'm going to verify. Was it really 0? Was it really 5? Well, if it was really 0 and 5, that's great. I don't need to do anything else. If it was not 0 or 5, then you have a problem. You need to redo the instructions. This is called value prediction. It's a fun idea, but it's tough to really implement, and it has limited benefits. And then we're going to talk about do something else. Okay, you have a data depends on this instruction. And you don't want to get into the situation that you have a data dependence. How do you design a machine that doesn't get into the situation of data dependencies? This is called fine-grained multi-threading. In this case, you ensure that the design of the processor is in a way that you never get into the situation of data dependencies. And this is also very fun. Actually, existing GPUs employ fine-grained multi-threading. We're going to see that heavily because GPUs have a lot of parallelism. You can basically say, I'm not going to execute an instruction from the same thread in the pipeline. Every single instruction in the pipeline will be from a different thread that I know is independent completely from each other. So there's no issue with data dependencies, control dependencies. I can safely execute all of the instructions in the pipeline without detecting it. And existing GPUs are good at doing that, basically. Okay, so we're going to see all of this, but let's talk about the detection part first. So a lot of these rely on detecting the dependencies, as you can see. And basically, we want to detect these dependencies. Okay, let's take a look at actually how these dependencies affect us in the pipeline and when we should detect them and how we should detect them. So let's take a look at this. So these are add operations. As you can see, this add is writing to register A, and all of the remaining adds are reading from register A. So all of the remaining adds are dependent on register A. So if this is the pipeline, you have a problem, right? These are cycle 1, 2, 3, 4, 5. You're decoding this instruction over here, and the first add has not produced register A. Write back happens over here. So you really need to delay the instruction. That's true also over here, right? Basically, these 3 instructions, if they proceeded in the pipeline, they would get the wrong values. Hopefully that makes sense. You're basically writing the value in cycle 5, but you're decoding this instruction in cycle 3. Well, that doesn't work because the value is not produced yet. And okay, there's an issue over there also. So basically, pipeline stall is one way of resolving the data dependence. Meaning, if you have an instruction that's writing to register X, instruction I over here, if you have the next instruction that's reading from register X, you need to insert some distance between them. You cannot execute the next instruction immediately or feed it into let it continue in the pipeline immediately. And the question of how much distance you should insert between them depends on how many stages of pipeline and what's done in each pipeline stage. Now we're going to assume that the write back is done at the last stage over here. And we need to have the value of the register. We can have the value of the register in the next cycle. But we're going to fix that with the register file trick that I told you earlier. So let's take a look. So clearly, something is slow again. Okay, clearly, we cannot do this. We cannot have this instruction in the decode stage and proceed while the producing instruction produces the value in time 5. So I need to insert a bubble, meaning stall this instruction in the decode stage and wait for the result. But that's not enough because the result is produced at the end of cycle 5. So I need to introduce another bubble in the pipeline. This is called the pipeline bubble, actually. But this is not enough also. So you have the instruction is writing back its result in this cycle. This instruction reading the register file in this cycle. Assuming you don't employ the trick that I showed you earlier, the instruction writes back in the first half and this instruction reads in the second half. Assuming that's not employed, you need to wait 3 bubbles so that the result of this instruction is correctly communicated, written to the register file, and this instruction, next instruction, reads the register file in the appropriate stage, reads the appropriate result. So basically, without the trick I showed you, you waste 3 cycles. So your pipeline throughput tanks, as you can see, right? This is not very good. Instead of really feeding instructions into the pipeline, we're waiting for the result to become available. That's why the trick I showed you is very good, actually. The trick I showed you, this instruction writes its result in the register file in this cycle, and this instruction can read the result that's written in this second half of the cycle, is great because it eliminates 1 bubble. So that's good. That's one way. With that, we eliminated 1 bubble. It's also called internal forwarding within the register file. If you read books, they will say that, okay, this is one way of forwarding the data value, internal forwarding the register file, but that's good because it eliminates 1 of the bubbles, but you still have 2 bubbles over here. Okay, so basically what we did, this insertion of the bubble is also called a stall. The idea is to make the dependent instruction wait until its source data value is available in the pipeline, in the register file in this particular case. Basically, to be able to do this, you need to stop all upstream stages. Upstream stages are earlier parts of the pipeline. You need to drain all downstream stages. And that's what we did, basically. We stopped instruction J, K, etc. And we ensured that instruction I finishes its write back. And once the result's available, we continue the upstream stages also. So you need to have hardware. You need to be able to do this in hardware or software, basically. That's the beauty of this picture right now. Who inserts these bubbles? Hardware can do that. Hardware can say, okay, I'm not going to move the pipeline because I've detected a dependence. We're going to talk about that dependence. Or the software can say, oh, I know exactly the dependencies. I'm going to insert bubbles, meaning no ops, no operation instructions. Basically do nothing. It's not very high performance, but they can do it clearly. Or software can say, oh, I'm going to insert some independent instructions. I'm going to analyze the program, find out what instructions I can put over there that are completely independent. That doesn't change the program semantics, and I'm going to put them over there. And that way, hopefully, you'll improve performance in a pipeline like this by distancing the data dependencies or dependent instructions from each other. So that's why this picture is beautiful. So let's talk about interlocking. So interlocking is the idea of detecting the data dependence, basically. It can be done hardware or software. Basically, you detect the dependence between instructions in a pipeline processor to guarantee correct execution. And there's software-based interlocking mechanisms and hardware-based interlocking. We're going to talk about this after we talk about the hardware-based first. But actually, MIPS acronym, what you're doing, MIPS, does anybody know what MIPS stands for? I think, yes. Exactly. Yeah, you get a brownie point. So microprocessor without interlocking pipeline stages, because you may not have heard that. Basically, that was their goal. When these people designed the MIPS ISA, they said, their philosophy was, their principle was, hardware is going to be extremely simple. We're going to put all the burden on software because we believe that we can do a good job in the software. And the hardware is going to be simple and fast, hopefully. It's going to be the responsibility of the software to detect the data dependencies and make sure wrong things don't happen in the pipeline. And that's what they said, basically. This ISA is designed to become producer of the microprocessors without interlocking pipeline stages, without hardware interlocking, they meant actually. Okay, but the software still needs to do interlock. So that was the goal, but reality is it's very difficult to do that in software completely. So all of the MIPS incarnations after the first ones have done interlocking in hardware. So their name was obsolete, or at least their name was not consistent with what they did in the end. Okay, so how do you detect dependencies? Let's take a look at some approaches to it. I'll go through these relatively quickly because I think these are simple ideas. Basically, you need to make sure the dependent instruction knows that there's another instruction that's going to produce the value that hasn't produced it yet, and that dependent instruction should not move in the pipeline. There are 2 major approaches. One is called scoreboarding. It's kind of like what you would expect. Each register has in the register file has a val bit associated with it, scoreboard. You can think of it that way. An instruction that's going to write to the register file at some point in time resets the val bit. For example, when you're decoding an instruction that's going to write to the register file in register 8, it says the value bit of register 8 is 0 because I'm going to change the value. This value is not going, it should not be read by any instruction until I reset the value bit to 1, meaning I actually write the value. Hopefully that makes sense, right? This is a scoreboard. You're synchronizing between instructions. An instruction in the decode state checks if all its source and destination registers are valid. This is how you detect all the dependencies, basically. If one of them is invalid, that means that there's some instruction in the later part of the pipeline that has not written up or updated the value. So it should stop. Basically, it should not move down the pipeline. Okay, so basically that's the idea. If all of them are valid, that means there's no need to stall because the register values are something you can trust. They're up to date in the register file, so you move on. But if at least one of these registers, 2 source registers and 1 destination register in the worst case, in some cases there are more than 2 source registers in some ISAs, but ignore that for now. Basically, all source registers and all destination registers, you check. And if any of them are invalid, you stall the instruction, saying that somebody is going to update the value. This way, you actually handle both true dependencies as well as false dependencies. Maybe you're just a bit more conservative with false dependencies. Yes, it is conservative, because maybe you don't need to stall the instruction if there's a false dependence, right? But ignore that for now. So the advantage is this is very simple, actually. Okay, hopefully we'll get to that. Yes, it's simple, 1 bit per register. But the disadvantage, you need to stall for all types of dependencies, not only flow dependencies. You can actually change this, modify this. I mean, the way I described it, you have to do it. You have to stall. But you can actually modify this a bit so that you don't stall for anti and output dependencies. But I'm not going to discuss that right now. We're going to discuss that issue more comprehensively when we move to out-of-order execution. But remember this is going to be our basis in out-of-order execution also, this data dependence detection mechanism. But this is not the only mechanism. So let's take a look at how this is handled. Each register has a valid bit associated with it. And for example, this load word, when it's writing to register 10, or when it's going to write to register 10, it says it resets the valid bit for register 10. And then when the subtract, if it's going to read from register 10, it checks the valid bit. If the valid bit is 0, then it says, oh, I cannot move forward. So you need to do something to ensure that this the subtract stays here. And we're going to see what that thing is. Basically, we're going to insert a bubble over here, a no-op instruction. And then we're going to ensure that no other instruction gets latched over here so that the subtract stays over here. We keep inserting bubbles until all of the sources and destinations of the sub become are valid. Okay, so that's one way of detecting. But there's another way of detecting, and this is what your book uses actually, a combinational dependence check logic. You basically add special logic that checks if an instruction in later stages or any instruction in any later stage is supposed to write to any source register of the instruction that's being decoded. This is a mouthful, but basically you look at all of the stages. Is there any instruction that's writing to the register that I'm trying to read right now? And if the answer is yes, stall. That's the idea. You detect the dependence. Right, I think I already said this. So how do you do this? By comparing the register IDs of the instructions that are in later stages to the source register IDs of the instructions that is in decode stage, and also checking whether the instructions in the later stage are writing to the register file and the instruction in the decode stage is reading from the register file. You need to do the right checks, basically. So the advantage is there's no need to stall on anti and output dependence if you do this. That's the beauty, because you don't need to stall on anti and output dependence. That's good. And because we're handling them, we're writing to the register file in order, meaning we're never doing out of order writing to the register file. So their register file is updated in order. The disadvantage is logic is much more complex than a scoreboard right now. And the logic becomes even more complex as the pipeline depth increases, basically. If the pipeline becomes deeper, 30 stages, wider, meaning let's say you're doing 4 instructions per cycle. We didn't talk about that, but you can actually fetch 4 instructions also. It's called superscalar execution. This becomes a huge logic, basically. That's why scoreboarding is actually also good. But your book, with a 5-stage pipeline, actually, this is not bad. And your book uses this, this combinational dependence check logic. But we're going to also revisit this when we talk about out-of-order execution. Okay, so basically, what is this? In a pipeline operation, what happens is this load word has a destination register ID over here, and it has a bit saying that I'm going to write to the register. That goes to another logic over here. And then also this instruction over here has a source register IDs, and it says I'm going to read source registers. And basically you have comparators. comparators basically check whether the destination register ID over here is equal to any of the source register IDs, and whether the instruction here is writing, and whether the instruction is reading from the registers, or it needs to read from the registers. And if the output says that, oh, there's a match between the registers, and there's a conflict, and this needs to stall, then you generate a stall signal, which is used very similarly. You basically insert a bubble into this register so that you don't move the subtract instruction. Oh, that's dependent right now, sorry. And then you basically ensure that the pipeline register over here doesn't get latched, so that the subtract instruction stays over here. Basically stall the pipeline. Okay, so this is detection logic actually. We're going to talk a little bit more about it, but what do you do afterwards? Once you detect the dependence in hardware, what do you do? Basically, dependence between two instructions is detected before the communicate data value becomes available. One option is to stall the dependent instruction right away, and that's what I kind of assumed. Or stall the dependent instruction only when really necessary, meaning forward the data whenever it's available. Stall the instruction at the point where you really need the data, right? Maybe decode stage is not where you really need the data. So we will see this soon. There may be other options like moving the instruction out of the way. That's the out of order execution we will see. So let me give you the idea of data forwarding and bypassing, and we're going to implement this in tomorrow's lecture. But basically, this is more aggressive than stalling. If we don't want to stall, can we forward the data or bypass? And the idea, the problem is a consumer or dependent instruction has to wait in the decode stage until the producer instruction writes its value in the register file. Basically, we do not want to stall the pipeline unnecessarily. And the observation here is that the data value needed by the consumer instruction can be supplied directly from the later stage in the pipeline, instead of only from the register file. Basically, you don't need to wait until an instruction writes to the register file. You can get the value from the ALU result, for example, or the memory output. So basically, the idea here is this: add additional dependence check logic and data forwarding paths, meaning buses, to supply the producer's value to the consumer right after the value becomes available, or maybe after you last it. Last is maybe better, actually, as we will see. So the benefit is consumer can move in the pipeline until the point the value can be supplied. So you get less stalling. Does this make sense? So let's take a look at an example over here soon. Okay, any questions on this? We're going to look at how to do this, of course, right? You may not, okay, maybe you may be wondering, okay, what if I cannot do this, right? There may be cases actually you cannot do it. And we will see a case when you have a load instruction followed by a dependent add instruction. We will not be able to do this aggressively because load value, because of the way we design the pipeline, load value becomes available and the memory stage, and the add value, add needs to do the execute stage in the immediately next cycle, and there's no way you can communicate that value without lengthening the clock cycle, as we will see. Okay, so these were the concepts, and let's go into more concepts and implement them also in a real machine right now. So I think I kind of told you this, but how do you implement the stalling? If you want to implement the stalling, you need to disable the program counter. So, okay, what is stalling? Basically, we're going to stall in the decode stage. That's what we'll do for now. This instruction, you've detected some dependence to some other instruction over here. You don't want to move this instruction. What does that mean? That means that whatever is before, upstream, in other words, this is like a river, right? This is the upstream, and this is the downstream, rivers flowing from the upstream to downstream. You need to disable that program counter is not incremented, and you need to also ensure that the instruction here doesn't change. That's it, basically. That way, you ensure that this part of the pipeline doesn't move. That's what this says, basically. Ensure stalled instruction stays in stage. And also, you need to do something about what happens. So this instruction over here is going to move to the next stage, and this instruction over here is going to move to the next stage. What happens to this stage? You need to insert an invalid instruction, basically, or no op, into the stage following the stalled one. So after this decode stage, you insert a bubble. This is called a bubble. So how do you do it? There are multiple ways of doing it. You can clear everything, do no harm. Basically, you can set the control signal such that the instruction does nothing, like a no operation. Or you can have an invalid bit saying that, oh, this instruction is invalid, right? Your book uses a clear signal, as we will see. Okay, so let's take a look at a row data dependencies example and how we actually do implement this. So here, one instruction writes a register as 0, and next instructions actually read this register. So you have read after write dependence, as you can see, S0. All of the instructions actually read from this register. So you really have a data dependence problem between all of these places. So you can eliminate this one. Once this instruction writes to the register file in half of the cycle, the other instruction will get the value in the second half. So this one actually gets the correct value. The subtract gets the correct value because of our assumption, this internal forwarding in the data register file. But add writes it into S0 in the first half of cycle 5, as you can see over here, and reads S0 on cycle 3, obtaining the wrong value. If you don't do the right thing, and will get the wrong value, or will also get the wrong value because it reads S0 on cycle 4. Subtract, because of our assumption, actually got the correct value over here. But we want all of them to get the correct value. So how do we do that? Okay. Okay, this is true only if the pipeline handles data dependence incorrect. So before we do it the hardware version, let's do the software version, because software version also quite intuitive, right? So compile time, compiler looks at this, or programmer, you look at this and you say, no, this add should not write its value before any of the dependent instructions reads their value. And to ensure that, what I'm going to do is I insert 2 no-ops. Meaning after this add, I'm going to insert 2 no operation instructions. They're going to flow through the pipeline, do nothing. But they will ensure that this AND gets into the register file read stage in cycle 5. That's the whole purpose of these no-op instructions. Makes sense, right? So our problem was this AND went into the register file read stage too early. Well, get it into the register file stage later. How do you do that purely in software? Assume that your hardware didn't provide any support like MIPS people envisioned. Well, I insert no-op instructions. I can control the timing, assuming that I know the structure of the pipeline in software. I can do that. I can ensure that by inserting no-op instructions, I can ensure that this AND gets the correct value, and so do other instructions. And that's the idea over here. Hopefully this makes sense, right? So of course, this is not great, right? Now you inserted bubbles into the pipeline, but instead of hardware inserting bubbles, you're doing it in software. So okay, the general idea is this. A compiler or the programmer detects these issues. Of course, to be able to detect these issues, they have to know the pipeline structure. So now your pipeline needs to be visible to the compiler or the programmer. That's one downside, clearly. And they insert enough independent instructions such that the correct or required result is ready by the time it's needed by a dependent instruction. So I'm not saying no-ops over here, right? I'm just saying independent instructions. No-ops are clearly independent instructions because they have no dependency no dependency to earlier instructions or later instructions. But no-ops are no-ops. They're not doing any work. What the compiler can do is they can reorder the instructions. They can basically say, okay, I'm going to look at the code. Oh, there's a subtract instruction that's independent of this add, and it's none of the other instructions depend on it. I'm going to take that subtract instruction from here at the bottom and move it up. As long as I don't change the program semantics, this is perfectly fine. And you did not waste any pipeline slots this way, right? That's called reordering or rescheduling instructions. I don't need to insert a no-op, basically. And if you find enough independent instructions, they can come from the bottom over here, lower parts of the program. They can come from the top parts of the program. This requires analysis of independence and dependence of instructions clearly. And branches complicate this. Other dependencies complicate this clearly. But if you find enough instructions to insert over here from the same program, then you get rid of the no-ops. And your pipeline is still high throughput, right? You didn't reduce the throughput of the pipeline. No-ops reduce the throughput of the pipeline. Okay, this is a very powerful idea, basically. And we're going to talk about this again later on. But basically, tomorrow, we will cover data forwarding. This is also called data bypassing. And the idea will be to forward the result value to the dependent instruction as soon as the value is available, if possible, to do this. And we've already seen the basic idea before, actually, just to jog your memory and let you think critically. Remember the data flow principles? Data value produced by an instruction is supplied to dependent instruction as soon as it's available. And the instruction that's dependent gets fetched when all of its data values or data operands are available. So adding this data forwarding and data bypassing brings a pipeline closer to data flow execution principles, actually. So the principle of data flow is data value gets available and gets forwarded to the consumers, and we're going to do that tomorrow. Okay, that's a great place to stop, and I'll see you tomorrow. Have a good day. Yep. Oh, I don't know what's happening. Oh, there's a chat. No. Okay, I should probably finish our